Hello students, welcome to All Force e-learning channel. This is K. Nageshwar Rao, Physics faculty. We are in session number 86. In the last session we have discussed about Ohm's law, resistance and dependence of resistance on various factors was discussed, isn't it? Let us have a quick glance on what has been completed in the last session. We have started with this equation V is equal to IR, and then we have come to a conclusion by few observations that resistance is directly proportional to L by A, and later it was written as R equal to rho into L by A, where this rho is coefficient of proportionality, which is named as resistivity. And later resistivity, resistance by replacing A and L with various possible terms, we have written resistance like this. R is equal to what? Rho into L square by V is equal to rho into L square D by M is equal to rho V by A square is equal to rho M by dA square. Like that, we have written equations for resistance, isn't it? Any of these equations can be used. It all depends on situation that you are dealing with. Okay, especially when the wire is stretched, you have to be very careful at the time. Considering that the volume of the wire is constant, you have to proceed with the solutions. Okay, so now let us discuss about one more situation. I am going to consider a cuboidal block, something like this. This is a cuboidal shaped wire. Let us say its length is L, breadth is B, and this is H. So this is H and this is breadth, this is L. Now I am going to name these faces. Here how many faces are there? 1, 2, 3, 4, 5, 6. 6 faces are there. So let us name these faces. I will call this face as 1, this as 2, this as 3, upper one, the bottom one as 4. This side whatever face is there I will call it as 5. The opposite face I will call it as 6. I hope you understood. I just named all the faces of this cuboid. Okay, there is a reason for naming so that we'll be able to discuss very clearly. So what I'm going to do is I'm going to talk about resistance offered by this block when current is traveling in different directions. You can even imagine coordinate system here just for our understanding. Let us say this is x-axis, this is y-axis, this is z-axis. If current is flowing along x direction, what does it mean? It is flowing, it is entering in phase 1 and it is leaving from phase 2, isn't it? Along this direction. If I say that current is traveling along y direction, if the current direction is along y direction, what does it mean? It means current is entering here at the bottom phase, which is named as 4, and it leaves from the upper phase, which is named as 3, isn't it? If I say that current is traveling along z direction, what does it mean? It is entering at this phase, which is named as 6, and leaving from phase 5, isn't it? Okay, so I'll try to find out how much resistance this body is going to offer if the current is along x direction, that is entering at 1 and leaving from 2, entering at phase 1 and leaving from phase 2. If this is the situation, irrespective of whatever direction, in whatever direction the current is flowing, resistivity it's constant. It depends on nature of the material, it depends on temperature, it depends on concentration of the impurities, it depends on what else, these kind of factors, right? I'm not changing all these things. So here rho is constant. What about length? We know that resistance is expressed as rho into L by A. So here length is just L only. Okay, I will take it as L divided by area. Which area you have to take? You have to take this cross section area. This cross section area is equal to, what are the dimensions of this cross section? H and B. So area will be HB, H into B, isn't it? Okay. Now I'll consider this one, R 3, 4. Let us say the current is entering at third phase and it is leaving from fourth phase. Okay, if this is the situation, again what will be the equation? Rho into along this direction, how much distance is traveled by the current? It travels a distance equal to height of this cuboid, isn't it? H. So here the length of the conductor will be taken as H along this direction. Okay, and what about the area of this upper face? Upper face has got length and breadth, isn't it? So area will be LB, and the last possible one is R65. So the current is entering at the sixth phase and it is leaving from fifth phase. Let us imagine like that. Okay, so rho into how much distance the current travels, or what is the length of effective length of the conductor along this direction, along the z direction. It's equal to B. So in the numerator you have to replace with B. See, this numerator position is occupied by length of the conductor, or the total distance up to which the conductor is extending. And in the bottom, what you have to write? You have to write area of cross section through which current is entering and through which it is leaving. Okay, this, let us say in whatever direction we take here, we assume that it is uniform. Okay, so here in this case R65, it is entering from sixth phase and it is leaving from fifth phase. Rho, and what is the length of the conductor along this direction? B. I am telling you again, don't get confused with this one. In case of a cuboid, by default we call this as length, but when I am looking at this picture with the current traveling in this direction, my interest will be, you know, the total length of the conductor, or the total distance covered by the charge. I will take it as B only. So here I will replace it with B divided by what is this area? This area is L into H. Okay, say let L is greater than, B is greater than H. I will imagine like that. So here, which is the largest one? L is largest one. Which is the smallest one? H is the smallest one. Now the question is, we were able to figure out different resistances in different directions when the current is traveling in different directions. Now in which direction it offers more resistance? In which direction it offers minimum resistance? If you wanted to find out that, you can do that. Here resistance is, you know, when you look at this denominator, you know, if denominator is large, obviously resistance is going to be small. If denominator is small, resistance is going to be large, isn't it? Now look at this relation, whatever relation I have assumed here, L greater than B greater than H. Product of L into B will be large when compared to product of BH. Here product of LB will be what? It's large. Product of B into H will be what? Minimum, small, isn't it? So look for the denominator where LB is present. Here LB is present. So this is large. If this is large, this one will be what? Minimum. So here R34 is minimum. Which one? R34 in the sense when the current is traveling from this phase to the bottom phase. Okay. And where this you know, area BH is present. BH is present here, H into B, isn't it? So these two numbers are small, right? In this order, this is bigger one, later this one is smaller one. So obviously LB will be, product of L into B will be large when compared to B into H, isn't it? So B into H, it's a minimum area. So if HB is a minimum, this R12 will be maximum. So R12 is maximum. Where is R12? So when the current is traveling along this direction, along X direction, it offers more resistance. That's how you can understand this picture. Okay, and we'll continue with the few other details related to this resistance. Okay. Now let us discuss about you know, some other points connected with the resistance. I'm going to define two physical quantities. One is conductance. What is this? Conductance. It is denoted with Z. It is denoted with Z. And it is defined as inverse of resistance, or reciprocal of resistance. That's how it is defined. Okay. If you have taken inverse of resistance, its units can be written like this, isn't it? Units of resistance are ohms. So inverse of ohms will be written something like this, isn't it? So these are the units of Z. Or you can write like this also, MHO. If it is ohm, OHM, inverse of ohm, MHO, like that. Or there are, you know, specific units for conductance, Siemens. Okay, and the other physical quantity that can be defined at the moment, at this moment, is conductivity. Conductivity is something, that deals with ability of a conductor to conduct current. So how well it is able to conduct the electricity. So that's what it deals with. It's denoted with a sigma, and mathematically it is defined as inverse of resistivity. So there is a relevance between these two definitions. See, inverse of resistance is conductance. Inverse of resistivity is conductivity, isn't it? If see, if this is the situation, since this rho is connected with R like this, R is equal to what? Rho into L by A. So from here, this rho can be written as R A by L, and if you replace it here, and this sigma conductivity can be written as L by R A. This equation is important. Okay, we can make a little bit analysis over here. So let us see what we can do. I will consider insulators. For insulators, what is the value of resistance? See, basically insulator is something that doesn't conduct electricity at all. That's how we talk about insulator, isn't it? If it is not conducting electricity, what does it mean? In the other way, you can say that it is offering infinite resistance. That's the reason why it is not able to conduct the electricity, isn't it? So for insulator, R can be taken as infinity. Now when you replace R with infinity, anything by infinity is what? 0. So therefore conductivity sigma is what? 0 for insulator. I told you the conductivity is what? Conductivity is something that gives us information about the ability of a conductor to conduct the current, and here ability of the insulator is how much? 0. It's 0 in the sense it doesn't conduct any electricity, isn't it? So if I consider a good conductor, for a good conductor, ideally you take R as 0. Honestly, this situation is not possible. Any material, whether it is very good conductor or whatever it is, okay, it offers some resistance. But relatively, when compared to several other substances, there are few materials which do not offer much resistance, or whatever resistance they are offering, you can consider that resistance as negligibly small value, and you can ignore it, and you can call that resistance as 0. You can say that resistance offered by the good conductor is 0. And in the denominator, if you replace R with 0, what you will get? Anything by 0? Infinity. So what does it indicate? It indicates that the conductivity of good conductor is infinity. Conductivity of good conductor is infinity in the sense its conductivity is large, extremely large. That's how you can understand this picture. Okay, and again this conductivity is connected with several other equations also. I'll tell you about those things. Let us proceed with the discussion. In the previous sessions we have derived one equation for resistance. While writing equation for Ohm's law, R is expressed in terms of mass of the charge, relaxation time, isn't it? Tau. In those terms it is expressed. Let me quickly obtain that equation and see what we will be able to do that. What we will be able to do with that. What is drift velocity? Drift velocity is expressed as E tau by m. That's how we express this drift velocity. And this E can be written as V by L, where V is potential difference across the conductor of length equal to L. Okay, and if you replace it here, what you will get? Vd will be EV tau by ml. That's how it gets modified, isn't it? And we all know that, in the previous sessions we have derived one relation between current and drift velocity. What is that? I is expressed as NEAVD. That's how it was expressed. This is the relation between current and drift velocity. And if you replace drift velocity with this equation, this I becomes NEA EV tau by ml, or NE square A tau by ml. I'll write this V separately. And from here, what is V by I? V by I can be expressed as ml by NE square A into tau, isn't it? And what is this V by I? It's our resistance, whatever resistance we have been talking about, isn't it? Now look at this equation carefully. I'm going to shuffle this equation a little bit so that some other discussion can be carried further. I'll write this equation as R is equal to m by N E square tau into L by A. And when you compare this equation with R is equal to rho into L by A, what is the coefficient of L by A? This is the coefficient, right? So here L by A coefficient is what? Resistivity is. It means that this resistivity is equal to what? M by Ne square tau. So that's how in terms of relaxation time, number density of the electrons and charge of the electrons, mass of the electron, you can write resistivity equation. So from these two equations, what you can write? Resistivity rho is equal to M by Ne square tau. Ne square tau. Let us make an analysis here also. Look at this picture. I already told you resistivity is something that depends on concentration of impurities, temperature and the nature of the material. Okay, it doesn't depend upon shape. It doesn't depend upon dimensions of the material. Okay, look at this picture here. M is what? Mass of the charge, electron. That's something which is constant. And E is what? The charge of the electron, 1.6 into 10 power minus 19 coulombs. That is also constant. Now look at these two parameters. N is what? Number density. See, number density of the electrons, it differs from material to material. Okay, valence electrons, availability of free electrons won't be same in all the materials. Okay, so here this rho is connected with N as inversely proportional to N. If number density increases, resistivity decreases. If number density decreases, resistivity increases, isn't it? So this number density is a factor which is something connected with the nature of the material. Okay, so for good conductors, plenty of free electrons are available. Obviously, number density will be high, isn't it? If it is a not that much good conductor, number density of electrons will be small, so resistivity will be high. So this relation between rho and N indicates that in fact, yes, resistivity is something that depends on nature of the material. So mathematically also there is a evidence available to say that resistivity is connected with what? Nature of the material. And there is another factor tau. With the tau also this resistivity is connected like this, isn't it? Inversely proportional to tau. Tau is what? Relaxation time. Relaxation time in the sense the time taken by the electron between two consecutive collisions, average time taken by the electron between two consecutive collisions, isn't it? And that is something which is connected with the temperature of the body, isn't it? Temperature at which you are maintaining the body. If the temperature is raised, what happens? Relaxation time decreases very quickly. It travels between two consecutive collisions, isn't it? So relation of this resistivity with the relaxation time indicates that yes, resistivity is a physical quantity that can be influenced by the fluctuations of temperature. That's what conclusion you can draw, isn't it? So whatever details we have discussed, preliminary details we have discussed about resistivity, its dependency on physical, various factors, those are right. Mathematically we have evidence here, isn't it? So that's how these things are connected. Now let us connect somewhere here conductivity also. Conductivity is what? Conductivity is expressed as inverse of resistivity 1 by rho. And what did we get for rho? This is rho, isn't it? So sigma is equal to inverse of rho will be Ne square tau by m, isn't it? Ne square tau by m. See, sigma is what? Ne square tau by m. See, I is equal to, relation between current and drift velocity. What is that? NEA VD. VD is what? NEA into, I will replace with this one, EE tau by m. Good. So NE square AE tau by m. And I am going to make a slight modification here. I will shuffle this equation. I by A, I will bring this A to the denominator, is equal to what? NE square tau by m into E, isn't it? And what is this I by A? I by A is current density, current flowing normally per unit area is taken as current density. So I will replace this I by A with J. We have already discussed about current density. And what is Ne square tau by m? Ne square tau by m is nothing but sigma into E. So this particular equation is called as microscopic form of Ohm's law. Microscopic form of Ohm's law. Okay, students. So this is how there is a clear network among all these physical quantities: water drift velocity, current density, electric field intensity, resistance, resistivity, conductivity. So all these things are connected like this. Okay, so you should remember all these equations. Now let us proceed with one or two problems. Okay. Now let us discuss about this problem. What is this? A hollow cylinder whose resistivity is given as 2.2 into 10 power minus 8 ohm meter, of length 3 meters, has inner and outer diameter as 2 mm and 4 mm respectively. The resistance of the cylinder is. So he is asking about resistance of the cylinder. So let us draw a small picture here. So he is talking about hollow cylinder, right? So let us say this is the hollow cylinder. What was said? The inner diameter is given. Inner diameter is 2 mm. It means inner radius R will be equal to what? 1 mm. That is 1 into 10 power minus 3 meters, isn't it? And outer diameter is given as 4 mm. So outer radius is how much? It will be capital R is equal to 2 mm. 2 into 10 power minus 3 meters. And what else is given in the question? Length is given 3 meters and resistivity is also given 2.2 into 10 power minus 8 ohm meter, isn't it? So he is asking for resistance. What do we know about resistance in relation with all these physical quantities? Resistance is expressed as rho into L by A. You have to be a bit careful with this denominator area. What is that area? Area through which current is passing, isn't it? And here through this empty space there won't be any current. So all that you need to do is you have to calculate this area. You have to find out how much area is this shaded portion, and this can be calculated very easily. How? The total area pi capital R square minus this area pi small r square. So this equation gets modified as rho into L by pi of capital R square minus small r square. That's how it can be modified, isn't it? So now let us replace all these terms with the given data. So resistance R is equal to rho is what? 2.2 into 10 power minus 8 into length is 7 into R square. Capital R square is 2 square, 2 into 10 power minus 3 whole square. So if you take square of that, you will have 4 into 10 power minus 6 minus small r square. Small r is what? 1 into 10 power minus 3. So you will have 10 power minus 6 here. So now these two things gets cancelled. You will have 0.1 here. 3 7s are 21. 21 into 0.1, you will have 2.1. And in the denominator, what you will have? You can take out this 10 power minus 6 common. So 4 minus 1, 3. 3 into 10 power minus 6. And in the numerator, you are having this 10 power minus 8 term, isn't it? So now you can. So what we get here? 3. 0.7, and if it is taken to the denominator numerator, you will have 10 power minus 2. So finally 0.7 into 10 power minus 2, or this can be written as R is equal to 7 into 10 power minus 3 ohms. So the resistance of this hollow cylinder is how much? 7 into 10 power minus 3 ohms. Let us try one more problem. Now let us discuss about this question. What is this? A copper wire whose resistivity is given 1.7 into 10 power minus 8 ohm meter is its resistivity, and density, this is what? Density is what? 8900 k's per meter cube, and an aluminium wire whose resistivity is 2.8 into 10 power minus 8 ohm meter and density is given as 2700 k's per meter cube, have the same mass per unit length. Mass per unit length. It sounds strange. Nowhere in current electricity we have discussed about mass per unit length, but no need to worry. Let us see how this information can be, we can make use of it. The ratio of the resistance per unit length of aluminium and copper wire is. So finally, what we have to find out? We have to find out ratio of resistance per unit length of aluminium and copper wire. Let us see. See, we know that resistance R is equal to rho into L by A, and I am going to shuffle this equation. R by L is equal to R by L is equal to rho by A. What is this? This is what? Resistance per unit length. I'll replace this with K. Okay, just I'm calling resistance per unit length as K equal to rho by A. So this is the relation. Anyways, so here resistivity data is given for both copper and aluminum. What about cross sectional areas? They were not given. Okay, so whatever rest of the data is given in the question, from that somehow we have to manage to get this area information with the given data. Okay, so what is our final task? K resistance per unit length of aluminum to copper. So K aluminium divided by K copper. So this is what we have to find out, is equal to rho aluminium by rho copper into A copper by A aluminium, cross sectional area of the copper wire and cross sectional area of the aluminium wire. Okay, so see here, let m is mass per unit length. Mathematically I will write it as m by L. What is this m? This is total mass. Total mass. Okay. And this total mass can be written as density is what? Density is equal to mass by volume, isn't it? So mass can be, this m can be replaced with density into volume divided by L. This V is not potential difference, it's volume here. And you can replace this volume with cross sectional area multiplied with L, and in the denominator also you are having L. LL gets cancelled, and finally this is our relation, m is equal to dA, density into cross sectional area. And here it was clearly mentioned both were having same mass per unit length. So this m is constant for both copper and aluminium. So here A is what? M by D. M by D. Or you can say that since m is constant for both the materials, you can say that A is inversely proportional to D. D is what? Density. Now I will make use of this data here. Okay. So how it can be written? Rho AL by rho copper into A copper by AL. Since A is inversely related to density, so in the numerator we will get density of aluminium, and in the denominator density of copper. Okay. So let me make a substitution. Whatever values are given, I will replace it here. Okay. So resistance per unit length of aluminium divided by resistance per unit length of copper. So K AL by K copper is equal to rho AL into DAL. Rho AL is what? 2.8 into 10 power minus 8 into DAL, density of aluminium is 2700, divided by K copper, rho copper into density of copper. Rho copper is 1.7 into 10 power minus 8 into 8900. So when you make a further calculation, 2.8 into 27, approximately you will get 75 here, and in the denominator 1.7 into 89 or 90. So approximately here you will get 151, something like that. So this is nearly equal to what? 1 by 2. So what is the ratio between resistance per unit length of aluminium and copper? It's 1 by 2. So this is the answer. So that's how you are supposed to answer the questions. If at all, if any strange data, unknown data, something with which you are so far not familiar, if you see such kind of information, no need to panic. You can make use of the data to convert into known scenario. What is known scenario? All that we know is we know about area. We don't know about mass per unit length and all. Okay, so this is how you have to solve. Okay, children.